Okay, so last time around, Arrow ended talking about k-means and clustering, meaning you got a bunch of data and you think it may fall into different categories. How would you determine what those categories are? And all our examples are 2D, like what's on the screen, because then you can look at it and see whether it's succeeded or not. And obviously the reason you use these methods is because you're using them when data are multidimensional and you can't visualize them well, and so you can't know whether your method is succeeding or not. It's hard to perceive what the geometry is when you don't know how to project it down in order to make it obvious. And he talked about where k-means will fail, and it'll obviously fail where clusters don't look like your model. If your model is little clumps that are near each other, so either your model effectively says nearest neighbor or prototype is the way you want to do your clusters, meaning you have a cluster here centered on where my finger's pointed, or where my pointer's pointed, and you have a cluster here and you have a cluster here, and then things are just kind of symmetric around that. So one way to think about that, again, is to use likelihood as your yardstick. But k-means basically wants each data point to get associated with the cluster that's nearest. And so effectively, as Arrow said last time around, it's effectively acting like your model is that each cluster is a Gaussian, that the Gaussians have diagonal covariance matrices, meaning they're spherically symmetric. No, not just diagonal. They're multiples of the identity, so they're spherically symmetric, and that they share covariance matrices. So it's kind of like Fisher's linear discriminant made even dumber, right? The Fisher's linear discriminant says, I've got these two categories, and they share a covariance matrix. I don't know what the covariance matrix is. I'll try to estimate it as best I can. And all the covariance matrices, well, the two covariance matrices for a discriminant, are the same, but I'm not going to assume they're circular. If they're circular, if you're doing classification, and if your categories are assumed to be circular, category 1, and did not pretest the markers. And category 2. So if they're assumed to be circular and the same, well, then the Fisher linear discriminant is the one perpendicular, and the vector that separates them is the vector between the means. Okay, so that's like Fisher linear discriminant dumbed down. That's the prototype model. Okay, so when you go to more than two categories, or when you are trying to learn what the categories are and you don't even know how many there are, so that's clustering. The dumbest thing you can do is like prototype, which is what k-means does. K-means basically says I want nearest neighbor, which means it's starting with a model that assumes that everything's spherically symmetric and that all the covariance matrices are the same. And so it fails, as Arrow pointed out, when you have a setup like this, right? Very obvious three clusters, but they don't share covariance matrices. And so there is an alternative, which is to effectively do what's called soft k-means. So soft k-means works as follows, and Arrow kind of mentioned it but didn't get to it last time. So first of all, it's part of a more general mechanism for fitting models to data that's called EM, which stands for Expectation-maximization. And we're not going to go over the full what is EM here. It's kind of beyond the level of what we're trying to achieve in this class. But as we'll see as to how soft k-means work, the generalization to EM is not far, because it's an example of an EM method. So what's the model for k-means, for soft k-means? The model for soft k-means is the same as this model, except generalized in the obvious way. There are a bunch of clusters. I don't know what the clusters are. I don't know how many there are, but each time I apply it, I'm going to assume a number. So I'm going to let k be 3, try to fit. Let k be 4, try to fit. And how to pick which k is the right one is another issue that one can talk about. But regardless, for each k, I'm going to try to fit a cluster, a set of clusters. So if I'm going to try to fit 3 to these data, hopefully I'll pick off this one, and this one. I'm not going to assume they share covariance matrices. I'm not going to assume the covariance matrices are spherically symmetric or are aligned with the axes, i.e. are diagonal. They can be full covariance matrices. There's different versions of the model depending on how loose you want to be about it, so I'm going to talk about the most general one. Now, it cannot be run unless you have enough data. So we've talked about the cursive dimensionality before, and we're going to talk about it again a little bit later today. But point is, if k is 3 and dimensionality is 40, not 2, but 40, so a covariance matrix is a 40 by 40 thing. Oops. It's not only 40 by 40, but it can sing. A covariance matrix is a 40 by 40 thing, which is to say, and it's nearly half. It's a little more than half full, so it's like 800 numbers, right? And so we have 3 clusters, so we now have 2,400 numbers we need to estimate. You need a hell of a lot of data to do that. So if you don't have a ridiculous amount of data, that will not be feasible. Estimating means is easy. You don't need a lot of data to estimate a mean, even in multiple dimensions. But to estimate a covariance matrix gets harder and harder as dimensionality goes up. In any case, let's assume that we're in low enough dimensionality, 4 or 5, and we've got many hundreds of data points, and so this might be feasible. So how does soft k-means work? So like regular k-means, it's an iterative algorithm. So let's remind you of how k-means works. K-means, you pick, let's say you're looking for 3 clusters, you got 1,000 data points, you pick 3 points arbitrarily to start off the algorithm. Maybe you pick 3 of the data points chosen at random. You do whatever you do. So you've got these 3 means, they're your candidate means. You then assign points to clusters. And in k-means, the way you assign is by nearest neighbor. You assign every point to the current candidate clusters, whichever one it's nearest to. So you've now partitioned the data into 3 sets. You take those 3 sets, you find the means of them all. Well, I could just put up the slide that does that. Just going back a little bit. K-means example, yeah. Okay? So you got a bunch of data points, they're unclassified. You pick 3 places, either arbitrarily or you pick 3 data points, whatever you do. You then assign them to whomever they're closest to. So these become blue, these become red, these become green. You now take the blue points and find where the mean of the blue points is. So this guy's going to move over. So this guy was over here, and now he moves down to there. And this guy was over here, and now he moves a little bit to the right. And this guy was way the heck down here, and he now moves up to the middle of the green points, the mean. And then you reassign the points to them again, and you repeat. And you do this over and over again, and eventually it settles down, and if you're lucky, it does something reasonable. Okay? So that's the iterate. So the iteration is define the clusters, which means pick their means, and then assign the data points to clusters, and then define the clusters again, find their new means, and then assign the data points to clusters. That's the iteration. It's 2 different things. So we're going to have the same exact iteration, except now we're going to soften it and make it probabilistic. So here's how it works. So first you're going to have to assign the clusters. And you're going to have to do something to get the whole process started. Frankly, I don't remember the usual way to start soft k-means. I didn't go re-study up on it, my bad. But you could do it like you do it here. So that you pick 3 points. So step A, pick k points. And for each, initialize the covariance matrix for each of them as well. So now a cluster is going to be a mean and a covariance. It's still going to be assumed to be Gaussian, but now it's not assumed to be equal covariances for the different clusters, and it's not assumed that the covariances are spherical or even that they're diagonal. Full covariance matrices. Obviously, one can have other versions that do less than that, but we'll do the most general one. Okay? So we pick an arbitrary starting point, just like we did with k-means. All right? And now, because those covariance matrices, we'll probably initialize them to be the identity matrix, because why not? We don't know anything yet. So that means they're all spherical, which means assigning points to the, so this next step is assign points to the clusters, and because the covariance matrices are the identity, that means likelihood is the same as distance, or 1 over the distance if you will, right? So max likelihood is assigned to the closest. So now it's going to start just like k-means. So now all the points are going to be assigned to whichever cluster is closest, but not exactly, because here's the first difference. Points are not assigned to clusters. Points are given a probability distribution of what cluster do they belong to. Okay? So let's say we've got this set up right here, okay? And we initialize with, two. So here's our setup, and we've got 2 clusters that we started with that I'm going to, for example, pick 2 data points. So I pick that data point, and I pick this data point, say. Okay? So those are my 2 clusters, and they have identity matrix covariance. So now for every data point, say for this data point right here, no, I'll pick another one. Let's say for this data point right here, it has a distance from here. It has a distance from here. I should have done that in red. Okay? So it has a likelihood of belonging to the first cluster based on the Gaussian distribution. The Gaussian distribution we now know because this cluster has that as its mean and an identity covariance matrix. So you can just write what is, so this data point, we'll call this data point P. So what's the probability, oh no, it's not called P because P will happen twice. Let's call it XI. So what's the probability of data point I given the mu of cluster 1 and the covariance matrix of cluster 1? That's just a Gaussian. We know its formula. It's a number. What's the probability of that data point given the other guy, the red one? So let's do it in red. mu2 and covariance 2. So we only have 2 clusters for now, and we are not deciding that this data point belongs to cluster 1 just because it's closer. Rather, we're going to give it a probability distribution across the clusters. We have these, if the clusters are all assumed equally likely, Bayes' rule, we're going to just give this guy a probability that is this out of the sum of these. So, there's a little bit of Bayes' rule in there. What we really want is the probability of cluster 1 given xi. We want a probability distribution across clusters for each data point. But Bayes' rule, we can use that with the likelihoods because the priors are flat. And so we're just going to take this over the sum of these 2 and that'll give it a probability distribution. If there's n points, we'll take this out of the sum of the likelihoods, and that's what Bayes' rule would give us. And so for each data point, we can compute a probability that belongs to this cluster, that cluster, that cluster. And all we need to be able to compute that is the means and the covariance matrices. Okay? So we now have each data point has a probability distribution across the clusters to which it might belong. So that was the next iteration. In k-means, they got assigned to the highest probability one. And you threw out all the information about how close they were to the other ones. In soft k-means, you don't throw out that information, you keep it. And so you keep, I kind of belong to this one, but I might actually be in this one, I'm not sure. And you keep that as a probability distribution. Okay, so now you have that probability distribution. Now we have to go back and characterize the clusters. Remember, that's what we did in k-means, is first we decided which points were blue, which were red, which were green, and then we figured out, oh, the blue points, here's the middle of them. Okay? So now we need to do that iteration. So step one is initialize, step A, I guess I called it, was initialize the covariance. Step B, assign cluster probabilities. Things like this. Step C, define clusters, i.e. compute mu I and ci for all the i's. Because the clusters are defined by they have a mean and they have a covariance. Here there's a subtlety. I'm not going to write out all the equations, but I'm going to give you the general idea. So last time in k-means, we had a bunch of dots that were defined as blue, and defining the mean of the blue was easy. You just have a bunch of dots, compute their mean. We want to compute the mean of cluster number 1, say, right now, mu1. We'd like to compute that. But we don't have dots that are assigned only to cluster 1, because every dot now has a weight. Here's how much I belong to cluster 1. So what kind of average do you think we compute? Elena? Say it out loud. Yeah, you compute a weighted average. That's all. Right? Every data point has a weight, how much it belongs to cluster 1. So use those weights. In other words, you don't add up, some xi vector for I belonging to cluster 1 divided by n for cluster 1. That's what we did for k-means, right? We took all the points that were in there, we added them up, and we divided by how many there were. So now we're just going to do a weighted average. So there'll be a weight, which will be the probability that point I belongs to cluster 1. And down here, we're going to have the sum of the probability that I belongs to cluster 1. Okay? So it's just a weighted average. Just each one gets multiplied by the weight, and instead of dividing by n, you divide by the sum of the weights. But we also need to compute a covariance matrix. So we now have a mean, and a covariance matrix is you subtract off the mean from everybody and you do that outer product thing that we use to compute covariance matrices, but we have to change that as well. How are we going to change that? Covariance matrix is kind of like an average. It's an average squared distance. It's a vector. It's complicated, but it gets divided by n. It's kind of like an average, except it's a vector times a vector outer product that gets computed as an average, gets added up, right? So what do we want to change about that? The answer's obvious. Just say it. How do you change the computation of the mean? What do we do compared to k-means? Just now. Yeah. So what do we want to do with covariance? Answer? Same thing. That's all. It's not rocket science, although the equations get a little ugly. But I'm not going to write out how you compute a covariance matrix. You've done it before. But basically, you've got to take the vectors that are in there and do these outer products and add them up. But now, instead of just adding them up, they're going to get each one, before it gets added up, it's going to get multiplied by how much do I belong to that cluster. And then instead of dividing by n, you're going to divide by the sum of the pi's that you just did. Okay? So that will redefine all the clusters. The clusters will now have a mean and a covariance. Then you'll go back to B. You now have a bunch of clusters. They have a mean and a covariance. And Gaussian formula. Each one gets a likelihood. And therefore, each one gets a probability distribution. Then go back here and redefine the clusters, recomputing using a weighted average, their mean and their covariance matrix. And go back and forth. Okay? So it's just like k-means, except we've softened. We don't forcibly assign each point to one cluster. Rather, we see how likely is that point to have arisen from each of the clusters as currently defined. That gives likelihoods for all the clusters. Turn that into a probability distribution, a bunch of weights that add up to 1 for that point across clusters. Then redefine the clusters, that's down here, redefine the clusters using weighted averages and weighted average covariant matrices instead of hard assignments. So the reason it's called soft k-means is because you're not doing hard assignments. I can only belong to that cluster. You're doing soft assignments, meaning a probability distribution. Now, I said this comes from a more general class of algorithms that you may run into later on, and you'll definitely run into in other classes called EM. It's a very powerful method of trying to fit models to data, where you basically you have a bunch of parameters that you care about, which is you care about doing clustering. The assignment to clusters is what you want to know when you're done. And you have a bunch of implicit variables that you don't know that perhaps are less important. And you iterate between holding one constant and fitting the other, and then holding that one constant and then fitting the first set. So that iteration between hold a set of parameters constant and fit the data, then hold some other things constant and go back and pick your max likelihood parameters, that's EM. And it has a way more general application. We're not going to cover it here, but that's why this is often, certainly in the books that I've taught from, this is kind of the easy first pass exemplar of what an EM algorithm is, because it's so easy to understand. It's just like k-means. You just don't make your decisions along the way. You leave them soft.
The probability of the mean and covariance is just 1, or do you have a probability for the mean and probability for the covariance?
The probability of the mean and the covariance. Where is this coming in?
There's the likelihood. So you have a conditional probability.
This is a conditional probability. We never flip it.
Yeah, but it's just
So in EM.
And then in the weighted average, you have just that probability, right?
Right. So this is the EM trick of not having a full model over everything, but of iterating back and forth between hold this constant as if it's fact, and then compute likelihoods of the other part. So we hold this constant as if it's fact, although it's going to change later, and compute this probability distribution. Then we hold the probability distribution fixed as if it's fact, and then compute these guys. So there's no clear underlying model of where were the means and covariances drawn from. I have a big hierarchical Bayesian model that has, here's clusters that could ever exist in my lifetime. Some covariance matrices are more likely than others, some means are more. This isn't that kind of a model. But rather, so you never end up needing in the math, you never end up using in the math or assuming in the math anything about a knowledge about what clusters could exist. So I suppose effectively, if you want to write this as a Bayesian model, you're acting like those are flat in some sense. But they never come up in the math because you never have a probability distribution across these in the math. Rather, you fix them as fact, and you get a probability distribution across these, and then you fix these as fact, and you pick the max likelihood ones of these, which are just the averages, the weighted averages that we did. Okay, so you never remember other means that could have been true. You just pick the max likelihood one each time, and that's what EM does. Other questions?
Can you write out explicitly how this weighted covariance?
Oh, you're gonna make me do that. Oh, you have to do that. Oh, you're a mean person. Okay. All right. You got a bunch of data. The data points I've been calling xi. So you got these, x1, x2. That's your data. M number of points I've got. And each one of those, and let's say we're only doing 3 clusters, and so there's a P1, comma 1, P1, comma 2, P1, comma 3, P2, comma 1, P2, comma 2, P2, comma 3. So this is a probability distribution that we computed in step B, which is this point might belong to cluster 1, might belong to cluster 2, might belong to cluster 3. And so I computed those three likelihoods, and I turned those three likelihoods, I divided by their sum, I turned it into a probability distribution. Okay? So this data point, for now, looks like it's 0.8 probability it belongs to cluster 1, 0.15 probability it belongs to cluster 2, 0.05 probability it belongs to cluster 3. Okay? Now I want to compute the mean and covariance for cluster 1, having done this in step B. So in step C, I want to do things like this. So I can now just simplify it, because I'm going to do this for every single data point. So sum over all data points I, probability belongs to I, and where, the data point's coordinates, and make sure that we are doing a weighted average, so we got to divide by the sum of the weights. So that's how we get mu1 for time set t plus 1. Remember, we're going to do an iteration. So the new estimate of the mean is that weighted average. So what you asked is, how do you get the weighted covariance? So in general, how do you get a covariance matrix? So when you estimate a covariance matrix, we're going to, what are the elements of a covariance matrix? So we want to take x I minus the mean, this is a vector, minus the mean of, say, cluster 1 and cluster 1 at the current time. Let's just make it t, okay? xi minus mu1 times t. All right, this is a column. If I don't do anything about it, I want an outer product. Let's go back to week 1. Where do I need to put a transpose? I want to get a covariance matrix. This is going to add into the covariance matrix. Which one of those vectors needs a transpose? I'm going to wait until someone says something. This could get awkward. Can I multiply a column vector times a column vector? No. Which one of them wants to be a row vector? If I make the first one a row vector, I have a row vector times a column vector, which will give me what? Do I want one number? I want a covariance matrix. So it's on the second one. I want an outer product. Put a transpose here. Okay, we're going to want to sum this over all data points. We're going to want to divide it by the sum of the weights. I need weights. What are the weights? Look on the board. They're already there. I want to take a weighted average of these outer products for all the data points, weighted by what? Probability. That thing. Pi1, Pi1. See, I could do it. It's possible. Not lost. Okay? It's like a covariance matrix. Add up the outer products of your data relative to the mean and divide by n. But now they have to be weighted, so you have to put the weights on them and you have to divide by the sum of the weights. The only difference between this and actual covariance calculation unweighted is unweighted, these are all 1, so the p doesn't arrive there, and these are all 1, and so you just write the n, or m.
So there's something about like n minus 1 things.
Bleh. That's whether we're doing max likelihood or whether we're doing frequent statistics where we want to be unbiased. You're going to have 10,000 data points before you bother doing this. Nobody cares. Okay, so that's soft-K-means. And for a problem like this on the bottom, it'll have no problem, right? I mean, it's not going to do anything like this, or at least it shouldn't, because it's going to have no problem recognizing that when I get a mean that's in here and I see who's closest to me, they're all spread out. And so I'll get an estimate of a covariance matrix that's bigger, that's higher variance. And so it'll have no problem having 3 clusters that differ in covariance. And if you do the full tilt one that we talked about, where you're estimating a full covariance matrix, not just a variance. If I have to estimate a variance, that's 1 extra parameter per cluster, no matter what my dimensionality is. If I'm going to estimate a variance per axis, then I'm going to have, number of extra parameters per cluster, which is the number of dimensions. And if I have a full covariance matrix, I'm going to have a number of parameters that's like the number of dimensions squared divided by 2. Okay? So, curse of dimensionality. As the dimensionality gets big, this full tilt method that estimates the covariance matrix every time ain't going to work. It's going to be way too noisy. You won't have enough data to fill up this matrix and have it be trustworthy. So that will be a problem. But I wanted you to understand the idea of it. And obviously there's simpler versions that make assumptions and require fewer parameters. Okay, so that's soft k-means.
So can you clarify, soft k-means?
Oh my God, there's actually a slide. Now, does that help? I don't know. I guess it does. Why does a covariance get a lambda instead of a c for covariance? Okay, that's kind of what I said. And it's not telling you how these happen, but I did. Okay, fine, it's all there. Yeah, okay, so that's the assignment probabilities. Right. Okay. You get the likelihoods and those are, yeah, fine. That's what I said. Yeah, and so here's an example where here's the data and where they really came from, I don't know what's with these yellow points. Are they outliers or they're a different cluster? In any case, you run k-means and it gets kind of confused because it has this kind of effectively equal variance assumption, so that once you have these two guys, it wants to draw the line halfway in between. But when you run this EM clustering, otherwise known as soft k-means, it recognizes these have smaller variance and this has bigger variance. And I like it's called the mouse data set because it looks like Mickey. Now, one obvious, to some, application of all of this is a problem that neuroscientists run into all the time, which is you have data coming in your wires, and you have an electrode in some animal's brain, and that electrode is not inside a neuron, it's outside neurons, and there may be multiple neurons near it that are activating it. And so you have this problem that you have this noisy data set, and it, they look like there's kind of 2 kinds of events you see. There's this big positive, negative positive event, and then there's this funny negative event. This looks like a negative one and a negative one. This looks like it may be 2 events, and I don't know which kind. And so you get all these events, and you want to assign them and decide, oh, I'm listening to 2 neurons, and this spike came from that one, and this spike came from that one. That's called spike sorting. So the idea is you apply some kind of threshold to decide where the spikes are. And so you take your long record and you split it into little pieces that then become little vectors that want to go into a cluster analysis of some kind. So that you can assign each event where the voltage ever gets, so this is possibly a threshold, this is a threshold. And so you basically pick off the events that pass some thresholds. Obviously you have to decide where to put the threshold. But once you reach the threshold, you put a little window either side of it. That's what these little dashed lines are meant to say, right? And so you now have them all centered in a window, so you don't have an issue about when do they start, although that's going to come back in a second, right? And so you now have these little vectors, n-dimensional vectors of your signal from here to here, from here to here, from here to here. You have lots of them, and now you want to decide, was this 1 neuron? Was this 2 neurons? And then I decide this spike came from that neuron, this spike came from that neuron. And so you can take that thing and take that n-dimensional thing, possibly do dimensionality reduction using PCA, so that you take those vectors, put them in a big matrix, do PCA, and say that almost all the variance is this vector plus this vector plus this vector, so you reduce it down to 3 or 4 or 5 or something. So you now have vectors that aren't, 100 long, but vectors that are like just 5 numbers. And then you can try and find clusters in that now low-dimensional space. Why do you do the first step? We want to do clustering now. We've reduced dimensionality using PCA. Why do you want to do that? What have I said multiple times in the last 20 minutes that would make you prefer to have fewer dimensions?
Just way too many. We get really noisy.
You get noisy because of what problem? You'd have to, well, we've gone in circles on the too many dimensions. Why is that a problem?
The covariance estimation.
Because if you want to do soft k-means, you can't because you have too damn many parameters you're trying to estimate from too few data. And so you want to reduce dimensionality so that the thing becomes not unwieldy. I mean, k-means doesn't have a lot of parameters. It has the means of the clusters as you define them. But nevertheless, if you reduce down to 5 dimensions and you have 3 clusters, that's 15 numbers you're estimating. If you don't reduce it, it's 300 numbers you're estimating. So it could be a problem. It would be really noisy out in the tails here where there's no spike, and the clusters will totally overlap, and so maybe you may be pushed around by noise in your data. So it's to your benefit to get rid of dimensions that are kind of orthogonal to your problem. And if you think there's not going to be that many neurons in there, reducing dimensionality will allow you to avoid that. So you reduce dimensionality using PCA, but you still don't know where the clusters are. So you can try to use k-means. But what happens if in that little interval there were 2 spikes, one from the first neuron and one from the second neuron? So that'll be a problem. If they always fired 10 milliseconds apart, then you'd get a cluster for neuron 1 firing, a cluster for neuron 2 firing, and a cluster for neuron 1 fired and then neuron 2 fired, and maybe one for the other order. So you have 2 neurons, but you might end up with 4 clusters. But if the relative timing is variable and somewhat random, because these are 2 not particularly correlated neurons, then all of a sudden, even though there's 2 neurons, you're not going to notice that there's only 2 kinds of events out there. And so you can try k-means, but k-means will probably get confused. So here's the idea. Suppose I have neurons, like this, and neurons like this, and they add up. And so now we're going to reduce dimensionality. So we've got principal component number 1 and principal component number 2, and we have cluster of when neuron 1 fired and cluster of when neuron 2 fired. But when they both fired, you ended up getting a tiny cluster for simultaneous ones down here. And you also, all these little teeny points are presumably you passed threshold, but you weren't either of them. So the point is, you want to discover that there's 2 neurons, but the method isn't really telling you that there's 2 neurons. But it's worse than that, because the second neuron, as I said, could occur at various different times. So these data down here aren't real data. These are simulated data based on sometimes pick this, sometimes pick this, and sometimes pick both with a random time interval in between. And now all of a sudden you get this kind of arc of data points depending on where the time was in your principal components. And so you don't really see clusters in the normal sense, which means you need a model. And soft k-means won't solve this either, because it's not like there's clusters and the soft defining won't be there. It's that there's something happening under the hood that you know about as a researcher, but that your model isn't taking into account of. There is a model that Arrow's a co-author on for this. Has the acronym for continuous basis pursuit. I'll give you just a feel for it. We're not going to go through all the math, but just to say that one can extend clustering even further based on a situation that you as an experimenter know. So here's the idea. Suppose, my electrode's in there, and it's catching some number of neurons. I don't know how many, but let's start with 2. So there's the black neuron, and there's the red neuron. And suppose the black neuron leads to some response in my electrode that, when it happens, it looks like this. And the red neuron, when it gets a response in my electrode, it kind of looks like, this, say. Okay? So they have different, voltage spikes that I see in my electrode per neuron, and they're also firing. And firing are events that occur. And you could think of them as maybe Poisson, you don't know, but they're events. So that this happens now, and now, and now, and now, and now. And this happens, now, and now, and now, and now, and now. Okay? Which means your electrode is going to be convolve this with this, convolve this with this, and add them. And then we're going to, do thresholds, pull out little events, and try and model it. Which means our model says that you might have two things, but they have time differences. And so you want to go back in your data and pick a set of parameters, two sets of parameters. What are these curves? And when did each kind of event occur? In other words, you want to solve spike sorting. You want to say, here's when the spikes were from this neuron, and here's when the spikes were from this neuron. And you have a model that is that. So that won't be k-means. It's going to be a fancier algorithm. The algorithm is going to be trying to do maximum likelihood across both what are the two waveforms and when did the spikes occur. It's going to need to know n, meaning how many clusters. Should I call it n or k? I forget. K-means. I guess I should call it k. So it's going to need to run for various numbers of contributors to the waveform, 1, 2, or 3. You don't have to look very far past that because no electrodes pick up that much, typically. And so the basis pursued is kind of pursuing these guys, which are the basis elements. So in linear algebra, we have this notion of a basis, which we've occasionally alluded to, although we taught linear algebra in a kind of a singular, non-algebraic version in this course. But when I, say, this is my coordinate frame, these are basis elements. What I mean by this is the coordinate frame is I can get to everywhere by adding these guys up with weights. That's what a basis means. And similarly, I'm getting my waveform, it's not on screen anymore. If I go back, I'm getting my waveform as noise plus these occasionally and these occasionally. So this at every possible time point and this at every possible time point is the basis for your measurements. Meaning, sometimes you get one of these, sometimes you get one of these. They usually get multiplied by 1, but it might be slightly bigger, slightly smaller. Not really, because neurons don't work that way. But it's still the idea of a basis, a set of vectors that you could add up with weights to get your signal, the measurement, the raw measurement you made. And so there is effectively a iterative procedure for estimating these and estimating these to do spike sorting that is in the paper that's alluded to here. Kanadam and John Crickillo and Eros Iancelli, and I forget who all else. Okay, I am going to suggest, given that I'm about to change to an entirely new topic, that we take an early break, because that makes sense. So, take 5. Recommends. When talking about that continuous basis pursuit thing a moment ago, that was a model of where your data may come from, which is a model that neurons lead to some waveform in my electrode, and neurons spike occasionally, and I may have more than one neuron. That was a model for where your data came from that was getting fit to data. So this general problem of fitting models to data has various pieces. So the model may have parameters, and we may want to estimate them. And we've seen this all semester long, where you formulate your model, but then you also have to formulate what you consider a good fit of the model, which means you need a cost function. These set of parameters fit my model, for my model fit my data better than these parameters. And so, for example, we've talked about maximum likelihood. So your data, if your model is stochastic, it has a probabilistic element in it, then data coming from this set of parameters will have a likelihood. data come from this set of parameters will have a likelihood, so you might pick the one that is more likely. You may have other cost functions in mind, but it's an optimization idea. But you also may want to ask about, how much do I trust the parameter estimates I got? Maybe I want to put error bars on them. Maybe I want to know, did it fit much better than other parameter estimates, and so on. We also may want to know, did the model actually fit the data very well? This may have been the best set of parameters, but it may have been a lousy fit to the data, and maybe there's a different model that would have been better than the model I had. And so you may want to compare different models based on likelihood or posterior. Likelihood is called the Bayes factor when you're comparing two models, or a posterior ratio for models. You may want to look for what kind of failures your model has. So you may want to say, okay, here's the model, and it was the best fitting model. Let's generate some data from the model and compare them to the data I started with and see if they look similar. So in order to talk about that, these are huge questions that one would do differently in different domains. What I'm going to do next is follow through on a specific example. This is a course where some of you are in neuroscience, and some of you are in cognition and perception, and some of you are master students, some of you are interested in behavioral data, some are interested in cognitive neuroscientific data, and some single cell data might matter for it. So we like to have examples that fit for both. And this one I'm going to act as if we're talking about a neural network model, but then I'll say that the entire technique also applies to behavioral data, and I'll talk about an example of that. So this is one that should hit all communities. So here's the idea. Suppose I have a neuron, and I'm measuring that neuron, and so the output of that neuron is a spike train. So that neuron spikes occasionally. And I know nothing about this neuron, and I'm going to have the human or the animal look at, images, and then I'm going to try to determine what this neuron's trying to do. So the goal is to say, if I give this stimulus, and the stimulus is a movie, a continuous change of a bunch of pixels, what's the probability that at any given moment I'm going to get a spike? And that's my model. And since it's a probability distribution for spikes, then when I actually get spikes, I can get a likelihood, right? Because I've got a probability of spiking each time, and I got spikes. And if I'm willing to assume independence across spikes, then I just multiply them together, I get a likelihood. Okay, so let's talk about a very specific movie, a really dumb, boring movie. So I have a neuron. Maybe it's in the retina, maybe it's in V1. Probably it's in V1, given what I'm about to tell you. My movie is going to be a bunch of pixels. The pixels will have gray values, and the gray values will change over time. So at any given time, I have 1, 2, 3, 4, 5, 6, 7, 8 pixels. And suppose this is a V1 neuron. And it's a V1 neuron that I already know is orientation selective, and it prefers vertical stuff. So I'm going to give it vertical stuff, but still try to learn more about it than just it likes vertical. And so my movie is going to consist of frames that look like this. Okay? So there are 8 pixels. They're stretched out to become vertical bars. Some vertical bars will be dark. Some will be light. Some will be mid-gray. There'll be different gray levels. Okay? So I got 8 gray levels, and that's what these are. 1, 2, 3, 4, 5, 6, 7, 8. Those gray levels are picked randomly and independently. You may occasionally see the term IID in some paper somewhere. It stands for independent, identically distributed. So every single little square in that thing for a new stimulus is chosen independently of all the others, and they're all drawn from the same distribution. And in the case of this stimulus, that distribution is Gaussian. So they're most likely to be mean gray, but they might be brighter than gray, they might be darker than gray. Okay? And the way we're going to represent this stimulus in numbers is not to say what's the pixel value, number from 0 to 255, but rather we're going to say what's the contrast. So in vision science, we generally refer to things in terms of contrast, and contrast is the value divided by the mean value on the screen. So if the mean, sorry, I said that wrong, minus the mean value on the screen divided by the mean value on the screen. In other words, if the pixel value is mean gray, its contrast is 0. If the pixel value is white, double of mean gray, then it's 100% contrast positive. And if it's black, it's 100% contrast, or contrast is -1. So contrast for typical stimuli like this is a number that ranges from -1 to 1, where 0 means mean gray. Now, why do we use this term? Because our model is going to be, that we're going to talk about in a second, is going to be one that doesn't have anything about adaptation built into it, but neural systems adapt, which is to say, if I put you in a dark room and have you look at stimuli that are on average, dark gray and only going a little bit above that, and then I take you outside and have you look at a monitor in a bright environment, neural responses will change. They will adapt to mean gray. So there will be a temporal dependency on what you've recently been exposed to that you adapt to. Contrast takes that into account by saying, what is the luminance of this piece of an image relative to what I'm experiencing lately? And so if I keep that thing I'm experiencing lately, stochastically average, constant, then adaptation is less of a factor. I'm not saying it's not a factor, but it's less of a factor because you're controlling adaptation by producing a stimulus that is mean gray on average, and that mean gray isn't changing over time. Okay, so now we have our stimulus. The stimulus is a bunch of random numbers picked from a Gaussian distribution, mean 0, meaning the average contrast is 0, the average pixel is mean gray, sometimes positive, sometimes negative. Okay, that's our stimulus. We're going to measure the output of this neuron, which means occasionally we get a spike. We're going to look at the stimulus before this neuron to see if we can learn what kinds of pixels, values, cause this neuron to spike. Okay? And so we're going to, assume that we know something about this region of the brain, and we know that there is some time delay. We're not going to look at pixels in the future because it's got to be causal. We believe in science. I am not affected by stuff that hasn't happened yet. So we're going to look at the past, but I'm going to look at a range of the past that seems reasonable, and obviously you can play with this and use bigger regions and see what happens, but a range of the past of typical temporal delays for this brain area relative to the visual stimulus on the retina. Okay? And so we're going to take a big enough range that I think I include all of what might affect whether I spike or not. And I'm going to, for each spike, I'm going to go back in time and say, what was the stimulus over that range just behind me? So this spike, I'm going to look at 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 this, and I'm going to take an average of what was the stimulus just before I spiked. And so that's called a spiked triggered average. And say, well, if that average says that when this bar was bright, 60 milliseconds later, there's a good chance I spiked. And when it was dark, there's a good chance I didn't. Then one might say this pixel is contributing to that neuron's receptive field, and it's contributing in an excitatory way. Bigger values led me to spike. Some guy over here, when he was illuminated 80 milliseconds ago, I tended not to spike. And so we'll calculate that by basically taking these little blocks of numbers and averaging them. And the question is, why would you want to do that, and is that reasonable? And what is it estimating? So the idea is, I will take each one of those time bins and say, here's a time bin, and neuron didn't spike. Here's another time bin, neuron didn't spike. Here's another neuron, it didn't spike. Here's another one. Here's another one. Here's another one. Pull all those blue. And then here's a neuron, oh, it did spike. I'll color that red. Okay, and I keep doing that over my entire epic of recording data. So maybe I record data for several minutes for this neuron, and these are, there isn't a time thing for us here, but let's say these are every 10 milliseconds, so this is only looking at 16 milliseconds in the past, or whatever it is. And so I've got, thousands upon thousands of these little time bins that I can look at, and that will either be painted blue because they didn't cause a spike at that specific time delay, or because they did. Okay? And so you do this over and over, and you get this. Well, this looks like a problem for what we talked about earlier this lecture and last time, right? This looks like clustering, and it looks like classification. Okay? And so one could, try and do classification, say, oh, here's a bunch of blue dots, and here's a bunch of red dots, and it looks like the stimulus going up this way led to dots. Now note, the space we're in is 1, 2, 3, 4, 5, 6, 8 times 1, 2, 3, 4, 5, 6. It's 48 dimensional. I'm only showing you 2 of the dimensions here. 2 pixels in that 6 by 8 rectangle. There are actually 48 of them. So you're not going to look at it like this and see, oh, there's 2 clusters. But you could, for example, compute the mean of these, which will probably be 0, and the mean of these, which would be something else, and say, okay, there's a vector. Maybe that's my receptor field. But one might want to justify that based on a model, and one might want to learn even more than that. So to do that, one needs a model. Now, you might say, okay, I'm in 48 dimensions. I have no idea what to do, so let's just build a full-on Bayesian model for this. So that these blue dots come from some mean and some covariance matrix, and these red dots come from some mean and some covariance matrix. If I'm willing to assume Gaussian, and maybe I want to get even fancier than that. And so one might like to say, what's the probability of a spike given the stimulus? Well, I can get the probability of the stimulus given a spike. That's right here, or given not a spike. And I might want probability of spike. Well, that's easy. I've got that in my data. I got spikes on 5% of time bins. So this I got. The probability of stimulus, I'm the experimenter. I determined that. So the only problem is modeling this bit. Okay? And this bit is probably a stimulus given a spike. And so let's say, spikes are only coming every so often. This guy's, for the stimulus is firing at, 10 hertz. So I'm getting on average 10 spikes a second. So non-spike events, I have lots and lots of those. But spike events, I've only got like 10 or 15 a second. And I recorded them for 5 minutes. So that's 10 times 60 is 600 times 5. Because I got 3,000 spikes. Okay? And I'd like to estimate all this stuff. Well, I have 3,000 spikes, and I'd like to estimate this thing. Now, this thing is not in 2 dimensions. It's in 48 dimensions. Let's call that 50 just to make a round number. Which means the covariance matrix that I'm trying to estimate is 50 by 50. Which means there's 1,250 parameters, give or take, that I'm trying to estimate. And I've only got, how many spikes did I just say? 3,000? So I'm going to estimate a covariance matrix with 1,500 free parameters when I've only got 3,000 measurements. It's just, that's not going to be a very good estimate. And the more dimensionality, the bigger a space of stimuli you play with, the more infeasible that's going to become. This is another example, as we talked about, a half hour ago, of what's called the curse of dimensionality. As it gets more multidimensional, just brute force estimating the model, and that's for a simple model. Multivariate Gaussian, you're making a huge assumption there. And even for that simple model, it gets to be really hard. So in order to beat that, we need to cut down the set of parameters, we need a model. So there are lots of possibilities of a model. I've got 48 numbers and I've got probability of spike, and I want a mapping from 48 numbers to probability of spike. 48 inputs, 1 number output. So I could do a polynomial. Now, I could do some kind of subspace, PCA, some fancy method for cutting down. I could try and build up a model. It's got some kind of stuff going on in it. So we'll talk about some of these in turn. But first, let's talk about the simple one, which is okay. Let's just do polynomial regression, right? Let's just assume it's a polynomial. I don't know what order, and let's see if it fits. Well, there's multiple problems with that. Okay. First order polynomial, otherwise known as linear multivariate regression. Well, that's going to have as output a straight line. I forgot that this was a build, but I guess it is a build. Yes, that is going to not fit what neurons actually do. Which is, as the stimulus gets higher and higher contrast, it does nothing, and then it fires more and more and more, and then it saturates. So fitting your data with a straight line or a hyperplane is not going to cut it. It's never going to be a very good fit. In fact, quadratic, third order, they don't fit saturating functions. You don't have a model that says, oh, I want a curve that looks like this. You have a polynomial. Not only that, fitting a polynomial is hard because let's say we want to do a quadratic. So that means we've got our 48 pixels. So we've got A plus BX1 plus CX2 plus DX3. Okay, so for the first order terms, I have 48 parameters. But then I got all the second order terms. X1 squared, X2 times X17. So there's 48 squared such parameters. It's as bad as the covariance matrix, and that's only for a quadratic. As soon as you get to cubic or quartic, the number of parameters just explodes. So Recursive dimensionality hits you again if you want to fit polynomials to data where the input parameter space is big, where the input parameter space is 8 pixels times 6 time steps. So that's not going to work for you. So you need a model. So here's a dead simple model. It says I only have 48 parameters, which is say I have a receptive field. In other words, I act like I know something about neurons. Neurons have receptive fields, and they do a weighted sum of pixels based on a receptive field. So they do a dot product with the receptive field, but then they need to produce an output. And inside neurons, the output as a fraction of the receptive field tends to look like this. It tends to look nonlinear in the contrast, and it tends to look inside the neuron accelerating, not like the curve I just showed you. So that's fine, and that's a nice model. So you have, and it's a model that should look kind of familiar, because what's a linear classifier? A linear classifier is project onto an axis, which is what this does, the dot product, and then apply a threshold to this axis. Well, this looks kind of like a threshold function. I mean, it's not going up to 1 and doing this. It's not doing an absolute threshold like we did in signal detection theory, but it's nevertheless, it's got low stuff that it's throwing away and high stuff that it's including. So it looks like some models that we have, and it looks like a classic model, very simplistic model for neurons that goes back to the 1940s. So, you know, McCullough-Pitts nets were, on a neuron, I take a weighted sum of stuff that's coming in, weight 1, weight 2, weight n, and then I have some kind of a threshold in me, and then I produce an output, and other neurons will get other inputs, and maybe those will connect to other neurons. That, as an architecture, is what deep nets are all about. The units look just like this. You know, so a ReLU, what's that stand for?
Rectify linear unit.
Yeah, so there's the linear and there's the rectifier. Okay? So ReLUs, which are the basic units of all of deep nets, whatever, are this model, except that you put them cascaded, lots of them, and lots of layers. So the only thing about deep is it doesn't just have 2 layers, it has lots of layers. So when I was a graduate student, Minsky and Papert, not on this list, came up with this book that talked about what they called perceptrons, which is this, just another name for the same thing. And they talked about what perceptrons could do, and if you only had a single layer, here's what you could compute, and if you had 2 layers, now you could do some more difficult stuff. We talked about that the other day when I, you know, set Arrow off on a tangent about the exclusive OR problem, where you want to separate out this classification from this classification, which you can't do with a straight line. But if you add a dimension, pull X out of the board, now all of a sudden there's a hyperplane that fits it. Remember that? So that this model can do. If you add this dimension, then down here you can do it. And so Minsky and Papert literally talked about the exclusive OR problem and other problems about what can you compute with these simple nets. And also how might you learn the weights was a big aspect of that, which wasn't really understood so much. And then a method came out for that, and neural nets got all popular in the 80s, back after I finished graduate school and came here, where all of cognitive psychology decided neural nets would be a model for everything, and they would learn by backpropagation. And then it kind of hit a wall for a while, and then people figured out that you could take, that if you had enough compute time, that if you had a net that had like 40 layers, you could still use backprop as long as you had enough data to train it. And now all of a sudden, you know, neural networks are running our lives. They're in our phones, and they're in those stupid airline, automatic response to things and so on. Anyway, so, you know, it's a perfectly reasonable, understandable model, but we need to do a little bit more to it to have it deal with spiking data, because this produces a continuous number on the outside, and we need spikes. So we just add Poisson. Okay? So now this puts out a continuous number, which is a spike rate, and then the Poisson distribution we've talked about in the past. Poisson distribution is, I know how many events per second So for each unit of time, I multiply by events per second times the unit of time, and that gives me, no probability of how many events in that little time bin. And if I make the bin small enough such that I never get 2, then I'm just getting a probability of getting an event in that time bin. Okay? So that's the Poisson distribution. Now, for each little teeny time bin, it'll produce spikes. So here's a very simple model. Now, you need no model for this. That's a known distribution. No parameters except for the parameter that comes out of this wire. This number is the parameter for the Poisson. But we need to estimate a receptive field, and we need to estimate a nonlinearity. And suppose we want to make no assumptions about this, and no assumptions about this, but that this is the wiring diagram. How would you get that from data? This is pretty much the dead simplest spiking model one can ever come up with. It turns out that it's really easy to fit to the kind of data we were just talking about. And I'm going to walk through that right now. And it's a descriptive model. It's interpretable. We understand what the pieces are. The linear receptive field, a nonlinear spiking nonlinearity, a spike generator. Now it's not mechanistic. This is not like a neuron that's got ion channels and biochemical interactions and whatever the stuff that neurons have. It's not done on that level. It's a big picture model of what a neuron's doing, but nevertheless, it's pretty easy to understand. So, assume that you do with your stimuli what I said you do, which is your stimuli consist of a bunch of directions that you're going to sample from. In this one, it's 8 pixels times time steps, but there's other ways to use it that still satisfy these assumptions. I'll talk about that a little bit later. But it's got, your stimulus has multiple dimensions. The distribution that you choose in that n-dimensional stimulus space is spherically symmetric. It doesn't have to be Gaussian. It just has to be spherical. And I'll come to why it has to be spherical in a moment. Okay? In other words, it's a function of distance from the origin. It's spherically symmetric. It doesn't have to decay like e to the minus x squared like a Gaussian does. It just has to be spherically symmetric. So you're going to determine, you're the experimenter, so you get to determine what your stimuli is. So you get to determine your stimulus statistics. And so what I'm going to do is take where the spikes are, take the stimulus back behind when the spikes are, like I showed you a moment ago, and average those little 6x8 rectangles. And I can show you that that's a good idea. Because it turns out that the spike triggered average, is there a slide for that? Or am I going to do this right now? Well, I'm going to do it with the next slide up. But it turns out that the spike triggered average, meaning you take those little 6x8s and just average them together, back behind every spike, is an unbiased estimate of the receptive field. Here the receptive field is being called W. It's a vector that gets dot product with your input, and it gives the thing that goes into the nonlinearity that leads to the probability of a spike. So that first receptive field can be measured by the spike triggered average, and it turns out we can also get an estimate of the nonlinearity out of this. And it turns out not only is this an unbiased estimate, but one can prove that it's the max likelihood estimate. So let's talk about that, but let me put the next slide up so that that's up while I'm talking about it. And let me get my notes so I'll do the notation cleanly. All right. So what's the spike triggered average? So the spike triggered average is I'm going to take all these red rectangles and average them. So I'm going to get a rectangle. Okay? I'm going to get a 6x8 by the time I'm done. Every spike, look back in time, grab the stimulus, take an average of those. So if you wanted to do max likelihood, what would I want to do? So where am I? Here we are. Okay. So to do max likelihood, I want to know something about, so first of all, what's the probability of a spike given a particular stimulus on the screen, where stimulus is a vector instead of 6x8 thing. Okay? So that's the kind of model that we'd like to have. And the receptive field gives you enough, in the model, which is not on the screen right now, so I should probably have the model up, which is receptive field goes to linearity goes to Poisson. Okay? So here's the probability of spike, and that is a deterministic function of what you get out of here, which means it's a deterministic function of take the receptive field and dot product it with your stimulus. Okay? So the probability of spike given stimulus is going to be something about dot product with the receptive field, if this model is correct. Okay? Now, in other words, this is some function f. There's f. Well, actually, f includes both of these things, but basically there's f of the receptive field, which on the slide a moment ago was w, so I'll go with w, dotted with the stimulus. Okay? That is the model. I'm just writing it down as math now. Okay? So we have this receptive field. I don't know what the receptive field is, but it's going to get multiplied and added point for point with the stimulus. That's the same as a dot product. And that's going to go through some nonlinearity, which I don't know what it is either. And that gives me a Poisson rate, which multiplied by the duration of a time step, that's going to give me the probability of a spike. Okay? So this f is both this plus knowing something about the duration of the time steps that I'm, what's the duration on my time axis. That's just a scale factor. Okay? So that's the model. Probability of spike given a stimulus is that. Okay, so now let's do Bayes' rule. So what's the probability of getting the stimulus I got on the screen given a spike, where again, stimulus, that's the 6/8 just before the spike, that's what I mean by this, is going to be do Bayes' rule, get probability of spike given the stimulus, probability of the stimulus, probability of the spike. Okay? And what's that? Well, I can substitute that in. That's f of w dot s. It's probability of spike giving a stimulus. Now, probability of stimulus. You're the experimenter, you know what that is. But there was one thing I told you had to do, which is you had to make it spherically symmetric. I didn't care whether it was a Gaussian or some other function, but it's got to be spherically symmetric. So spherically symmetric means it depends on how far the stimulus is from the origin, and doesn't depend on anything else. All things that are equidistant from the origin have the same probability. So it's some function g of the length of s, or the length of s squared, I don't care. Okay? That's just the definition of spherically symmetric. Now, if g is e to the minus, thing squared over 2 sigma squared, then that's Gaussian. But I don't care if g is that. It can be anything that's spherically symmetric, and that'll come in the proof as I show it to you. And then what's at the bottom is just the probability of spike, which is the firing rate that your stimuli produced, r. Okay? All right. Now, now, what's the, so now that's the probability of a stimulus given a spike. Now, we are going to do a spike-triggered average, which means we're going to take all the spikes, get the stimulus, and then take their average, which means we're computing an estimate of what quantity. This is a probability of stimulus given a spike. This is a probability distribution across all stimuli. Stimuli are 48-dimensional, and so we're in a 48-dimensional space. It's a huge space. It could be bright over here. It could be dark over there. Lots of possible stimuli. Across that huge 48-dimensional stimuli, we now have a distribution. Now we're going to take a bunch of these actual ones from the thing and average them together. So when you average together these samples, what is it you're estimating? That average, if we calculate it forever, infinite amounts of data, and we average all the stimuli that happened when there was a spike, what are we going to get in notation? When you take an average over a random process for a long time and calculate some function on that process, what are you computing? It's got a name. We're using it all semester since probability theory started. So my Gaussian, I don't know what its distribution is. We're just computing an average. Except an average over the full population, not over a sample. An average over the population is called an okay, now we're at the letter E. It's called an expected value. Thank you very much. Give that man the cutie doll. Okay. It says expected value. Okay? So we are doing this thing with data, which is average a bunch of stimuli together. Why would you do that? Because you're computing the expected value of a probability distribution. Okay? So let's think about what that expected value should look like. Okay. So that expected value, first of all, is how do you calculate an expected value? You calculate an integral over all possible stimuli of the probability of that stimulus occurring times the thing we're taking the expected value of times the probability of that stimulus given spike. What I just wrote down is the definition of expected value. It says, here's all the S's that could occur. They have a probability, and the thing we're averaging has a number. And so we're doing a weighted average of these across all of these. Okay? Oh, sorry, there's an S in there. Yeah, I left out the S. We're averaging the stimuli weighted by their probability of occurring. Yes, it is like, yeah, there we go. Why am I putting an extra chart? It's in here. That's in there. Never mind. So we're averaging across stimuli weighted by their probability of occurring. Now, the probability of occurring, that's this thing, which I just wrote out what it is. It's right here. So this factor that we're talking about is this thing. Okay, so now I want to talk about the geometry of that thing. Okay, so S is 48 dimensional. Obviously, I'm not going to plot 48 dimensions. I'm only going to plot 2 of them. So here's 2 dimensions. So here's S number 1 and S number 2. There's 3 up to 48. I'm only giving you 2 of them. Now, I want to take a weighted average of all the S's. Here's the S's. I'm going to take a weighted average of all the points in this space, but they're going to get weights that come from this, which is this. And this has a constant on the bottom, which won't affect anything. And then it's got these 2 terms. So one of the terms is the stimulus ensemble, which is spherically symmetric. And in particular, just to make things simple, S1 and S2 are in contrast terms. And the average contrast is 0, which is the origin here. And it's spherically symmetric, which means that if I draw some circles, what are these circles? What name do they have? They're contours. What kind of contours are they? What is true of all the stimuli on one of those circles? As stimuli. Those circles, the data points are stimuli, S1 and S2. And all the S1s and S2s on one of those circles share a property. What is that property? Second term is a function of vector length. All those points on a circle have same vector length, which means they're all equally probable. Those are equiprobability contours for the stimuli. In other words, in this Bayes rule calculation, P of S is constant on one of those circles. Every one of those stimuli is equally likely to show up in the stimulus ensemble that you're generating the way you're generating it as every other one. Okay? That's what I meant by spherically symmetric. Okay? So that's number one. The other one is the probability of spike given a stimulus, which is a function of W dot S. Okay? So W is a vector in the same 48-dimensional space, which means I can draw W. I don't know what it is. We're trying to estimate it. But let's imagine that W is this vector. Okay? And there's some function of W that's going to get multiplied by G, and that's going to get weighted average all the points in this space. Okay? So that's what we're doing. In computing the spike-triggered average, we're estimating the expected value of the stimulus given a spike, and we're going to integrate over this whole space two things. A function of what's the stimulus's dot product with W, that's this, times the probability that stimulus showing up. Okay? So here's W. I'm going to draw some perpendiculars to W. Now, along this perpendicular, what is true? What's a fact about everybody on that line? I drew the line, not arbitrarily. It's a line that's perpendicular to W. So what does that mean? What's the trait that every point on that line shares? Vis-a-vis the model that we're talking about. Hmm?
The dot product with the point.
Vectors down this way will definitely have a zero dot product with W. But these guys, vectors that are all on this line, will not have a dot product that's zero, but what is it about their dot products that's special? On one of those lines. What's a dot product give you?
Projections.
Right, the projections are equal. Exactly. Okay? W dot S is constant along any one of these lines. They are lines of iso dot product. Okay? So let's pick one of these lines. Let's pick, blue one? No, blue one was bad. It's the red one. So let's pick a particular one. Let's pick this line, right here. Make them red. Okay? And this line intersects the big old circle here and here. Okay? So we're going to take a weighted average of stimuli, weighted by these terms here. And in particular, those 2 points are going to contribute to the average. Now those 2 points have the same dot product because they're on that line. So this term is the same for both of those points. This term is the same but for both of those points because they're on a circle. Which means those 2 points have the same probability. Which means in this integral, this is the same for these 2 points, and so they're both going to contribute equally. One of those points is a vector pointed down here this way. One of those points is a vector pointed down this way. They're going to get the same weight, and they're both going to contribute. So their joint contribution is going to be parallel to what vector in this diagram? We're doing a weighted sum of vectors. This will get a weight, this will get a weight, they'll get the same weight. We're going to add them both in. Which way is their sum going to point? It's visible there. Yeah, it's going to point along W. Right? Because this is symmetric with respect to W. I chose it that way. The diagram shows that it's that way. Every single point on the whole plane has that property. All of the things that you're integrating over, you can split it into an integral of the stuff on this side and the stuff on this side, and those will all get equal weight symmetrically, which means that the net response, by the time you integrate over every vector in the whole damn plane, has to be parallel to W. Which is to say the spike-triggered average is an estimate of W. Now, receptive field is a direction in space. It doesn't really matter what its length is, because remember the model, oh crap, I erased the model again. the model is receptive field, nonlinearity, Poisson. If I multiply the receptive field by 2 and I divide the nonlinearity by 2, I get the same model. So I never really cared about the length of W. I cared about the direction it was pointing, which gives me the shape of the receptive field. So by the time I'm done with this thing, I'm getting W. Okay? And if points on this side give bigger contribution than points this side, the W will point in the right direction. So this gives us an unbiased estimate of the receptive field. Spike-triggered average is not a silly thing to do. It is a reasonable thing to do based on a model that's estimating something that you wanted to know. When will this fail? What could happen here that would be bad, that wouldn't give you an estimate of W? I've just told you that everything's, you got to choose the stimuli. So this circle thing is a known. Let's say that you know, one of the elements of the model is compute W dot your stimulus. So the first element of the model, this thing, is also true. Okay? What would break this model? When would you not get an estimate of W? What could happen such that by the time you multiply it and add it up, you didn't get an estimate of W? Well, you're always going to get a vector, and I just told you that it should point in the direction of W. So what outcome would be useless and would screw you up? Because I've told you, you're going to get a vector that's pointed in W's direction. What could happen to that vector to make it so that, ooh, 10, I don't know W?
0.
Yep. So if you got 0, you're screwed. When would you get 0? There's no problem with this bit. I'm telling you, this bit is what I said it is. So what problem would this cause to give you 0? Give me an F that would give you 0. The simplest version of F, nonlinearity, that would give you 0. Meaning, you're getting components that look this way, but you're also getting components that look this way, and they're all canceling out. What value of F, what function F would do that? Simplest one. Actually, there are two simplest ones. Depends on your definition of simple. What would give you the same contribution for things pointed that way and things pointed that way? I couldn't hear that. Say it louder, whoever's saying it. Don't be shy.
Absolute value.
Absolute values, or x squared. Okay? If f is an even function, meaning same contributions for positive things and negative things, then it'll cancel out. Because you'll get vectors this way from these two, and vectors this way from these two, and they'll get the same weights, and so they'll all cancel out. So, in other words, spike-triggered averaging is very fine for a simple cell, and will fail for a complex cell. And you'll need a more complicated model, and you'll need to do something slightly different than spike-triggered average, and we'll talk a little bit about how you might do that in just a second, just as a brief example. But for anything remotely like a simple cell, where the nonlinearity is not even, you get big responses when the input's positive and small responses when the input's negative, it's a perfectly nice thing to do. Okay, so, so this W that we get out is a vector in stimulus space, which means it's a stimulus. It means a receptive field, but it's in stimulus space. You can plot it as an image. And so if this is the W you get, it's saying, I like bright stuff here, and I like dark stuff there. It's saying, remember these are vertical pixels. I like the middle pixel to be vertical 30 milliseconds ago, and this pixel to be bright 40 milliseconds ago, and this pixel to be bright 50 milliseconds ago. In other words, this neuron is what? It's direction selective. It likes something that's moving that way, which I'm assuming means, oh my stimulus disappeared, but I assume it means leftward. But I don't know, I've never told you how I plotted it. Okay? So you get a space-time receptive field out of this thing. What changes here? And now what we're going to do is, okay, we've got our receptive field, and we have all our stimuli that produce spikes and all our stimuli that did not produce spikes. And so we can project them onto this axis and say, when I got a W dot stimulus, which we now know what W is, so we now know what W dot stimulus is. When did I get spikes and when didn't I? So we can project down onto that axis and then histogram and plot it. So if we do that, we get this. So this is the spike-trigger average response, otherwise known as the receptive field that you estimated, dotted with the stimulus that was on the screen. And here's the histogram of what its value was when you didn't get a spike. And here's the histogram of what its value was when you did get a spike, where we have normalized those. And so question is, we now want to know F. And every time it was this value, you didn't get a spike. And when it was this value, sometimes you got a spike, but much more often you didn't get a spike, which means the probability of spike is low. And way over here, when you had this value, you always got a spike, which means the probability of spike is high. Which is to say, a ratio here, properly normalized, is F. So you can actually estimate F also. Now that estimate is going to be really noisy down here where you have very little data, and really noisy over here where you have really little data, because you remember your stimulus distribution was spherically symmetric, and typically, low pixel values are high probability, and high pixel values both negative and positive or low probability. So out here you didn't have many stimuli that were way the hell out here, and much more of them in the middle, because that's typically how you pick them. But the point being, you can effectively take this ratio and say, okay, here's F. Now you can be fancier about it and have a model for F that has to have a particular form with a small number of parameters, because this model is basically any value at any time step. So this is a parameter-free estimate of F. So now we've nailed down the entire model. Receptive field, nonlinear, Poisson, we got the whole thing. With an unbiased, in fact, for Gaussian stimuli, max likelihood estimate of the receptive field, and a good estimate of the nonlinearity as well. And so now we've got all the elements, because, as I said, we want the probability of spike given a stimulus, and we've got probability of stimulus given a spike and probability of stimulus given no spike. So we have all the elements to compute that thing using Bayes' rule. Now we may ask, how good is our model? Now, there are lots of ways to do this. One way is, instead of projecting onto W, project onto something perpendicular to W. Now, we're in 48 dimensions. W is one dimension, so there's 47 others. 47-dimensional null space of W, okay? So there's lots of places we could project to. It's a whole hyperplane, but you could pick one or pick lots of them and project onto them and see what you get. And what you, so here is, one arbitrary one perpendicular to W, that line, and we can project onto it. And the idea is that's a null space. That should not affect probability of spike, and in point of fact, d prime of 0, right? That axis, and in fact any of the axes perpendicular to W, should give you this if your model's correct. If the sufficient statistic, I think I used that term much earlier in the semester, if knowing how often the guy is going to spike is entirely a function of W dot stimulus, and there are no other statistics on the stimulus that need to be computed, if that's the only thing you need to know, then this should always be true. What comes next? And the ratio, so if you try to get a function on that, you get nothing, because the ratio is basically always 1. Now, so let's follow this through. So let's apply this to some neurons. So here's some ganglion cells, here's the model, we've got some spikes. And we do this thing, same math we were doing on actual data, and you get that this guy is an on-center off-surround, this guy's an off-center on-surround. You get, you're doing this over so this is a, array, spike-triggered averages, multiple slices in time. So this is one slice in time, a different slice in time. This is a slice in the time axis without space for various different pixels. So you get that, recent bright lights excite me, but further in the past they inhibit me. So you get a temporal response function, and you get a spatial response function, and you get a convex nonlinearity, which is typical for neurons, followed by Poisson. So one can go off and measure receptive fields and measure spiking nonlinearities. But now you can ask, is my model really working? because now you got the model. So now you can take the same exact stimulus you showed to the neurons, not one like it, the exact one, because you remembered the seed your random number generator had, so you can generate the exact same set of pixels in the same order again, and then run it through this model. So this model is not deterministic because it's got this. So you could run it multiple times, but you can get spike trains from this model just like you got from the neurons. So here we are with that. Here's the ganglion cells, and here's the model. And they look similar. You know, when this one spikes, this one spikes. When this one doesn't spike, well, spikes once in a while. And, you know, this one spikes and you have these two obvious sort of temporal behaviors going on in there. And here just, you know, it's mushy, right? So it looks close to the data, but it ain't right. And so the question is, and here if you just, you know, over multiple runs with the same stimulus, you can actually use the same pseudo-random stimulus multiple times, which is what's happening here. And you're running the neurons on the same spike multiple times, and you're running your model with its Poisson spike generator multiple times. So you can take an average, where black came from the data and red came from the LNP model. And, you know, they're close. They peak at the same places, but this has spikes where the data never had one, and when the data had spikes, it's not generating quite as many. It's just not quite as synchronized as you might like it. So we'll get back to that in just a second. But you see, you know, covering 74% of the variance, a decent model. But clearly, there's room for improvement. And you can run it on all kinds of neurons. So here it is running on V1 simple cells. So here's different time bins. And you see what looks like a simple cell receptor field. And this obviously had a gazillion parameters, not 6 by 8, because this is a big spatial array and there's multiple designs there. So way bigger dimensionality here. But nevertheless, it sees that it's a spatially organized receptor field that prefers vertical stuff. You also notice that the green thing is moving rightward as you go back in time, which is to say that this is another leftward preferring neuron. It's a direction selected neuron. Here's a, you know, so it's a big cube of numbers that you've estimated. So these are spatial images. They're vertical slices here. But you can also take a horizontal slice and get a slice in space and time. For those of you to perception, when you did the motion section, you've seen these. And you see that it prefers motion. You know, this is at 300 milliseconds in the past, and it prefers leftward motion. Okay, so it's definitely a useful technique. Here it is being applied to a number of different cells. And once you get this big 3D cube, you can take that 3D cube, that three-dimensional receptor field, and plot it in space-space or in space-time and see aspects of that. You can also Fourier transform it and find out that this neuron has a spatial frequency that it prefers. It's a bandpass filter. These are 3 different neurons. And you can give it a, you know, do a temporal aspect of the Fourier transform and find out it has a particular temporal frequency that prefers, say, 1 hertz. And so you can learn all kinds of aspects about neurons' behavior in the space-time domain or in the Fourier domain from what you get from the spike-triggered average. You can also use this. Everything's been neurons all day, but this is also used for behavior. This comes from Richard Murray, who spent about a year and a half as a grad student, but he's got this elastic band between him and Toronto, and every time he's tried to go somewhere else, he sprang back after a year or two. He's at York University in Toronto these days. And he often uses what's called classification images to study behavior. You gotta be a little brutal attitude towards your participants to do classification images. I do psychophysics in my lab. Typical experiment per subject. You know, they're in the dark room pushing buttons for an hour, or maybe 10 hours, maybe even 15. To get a classification image, it's the behavioral equivalent of a spike-driven average, except the spike is I push the yes button versus I push the no button. Okay? So it's not 10 milliseconds, it's the several seconds per trial that it takes to run psychophysics, but you still need the 10,000 trials to get a good estimate of a classification image. And so what you see here is I asked subjects, was it a vertical stripe or a horizontal stripe? Except I didn't show them the stimulus, I showed the stimulus plus a hell of a lot of noise. And so the stimulus is the stimulus plus the noise. Okay? So you're looking at these god-awful images saying vertical versus horizontal, and you're hitting the vertical button or the horizontal button each time. And so if I call vertical noise and horizontal signal in the signal detection theory sense, because this is a two alternative forced choice task, I've got all the outcomes of a two alternative forced choice task. It was a vertical, but I said horizontal. It was a horizontal, and I said horizontal. It was a vertical, and I said vertical. It was a horizontal, I said vertical. So hits, false alarms, misses, correct rejects, they're all in there. And now, I ignore the stimulus, but I just take the noise that was added to the stimulus associated with the times I hit the 2 button minus the times I hit the 1 button. So I'm asking, when this noise pixel was white, did that push me towards hitting the 2 button? How much? By doing a spike triggered average, but it's not spikes, it's button presses. Okay? And what comes out of that is a relatively sensible looking image, which says, when it was bright where the horizontal thing's bright, when the noise was bright where the horizontal thing was bright, I was more likely to say it was a horizontal. When the noise was dark where the vertical thing is bright, I was less likely to hit the horizontal button. But I also got some contributions from other places, so I was not an ideal observer. An ideal observer doing this task would have white here, black here, and everything else would be mid-gray, meaning a value of 0. And that's not what you got. Now, some of that is noise in estimation, because this can't be perfect. But part of that is actually signal, meaning that their template that they were using was not an ideal template. It was close, but not perfect. An example of one that shows you that you're not perfect, and an example of extending this beyond the linear dot with W notion is this one. So now you're looking at a movie. It's a bunch of vertical bars, and they're flashing over time, and they go for they go for 10 time steps, which is 2 seconds, so they're changing every 200 milliseconds. And you're supposed to say, when was the middle bar, when was the middle bar in the middle of the sequence bright? That's your task. You're even giving feedback, whatever. You do this a gazillion times with noise added to it. So the stimulus is a brief flash in the middle of the sequence of a bright bar. And so an ideal observer would have a spike trigger average, which would just be a 1 here and a 0 everywhere else. And what you get is there's a lot of uncertainty in time, and so they're affected by noise that's after what they're supposed to judge and before what they're judged. And you also get these regions on the sides, which shouldn't surprise you because of the fact that perceived luminance doesn't just depend on the luminance where you're making a judgment, but it depends on the luminance on either side, otherwise known as contrast effects. Meaning, if I'm a gray thing surrounded by white, I look brighter. If I'm a gray thing surrounded by, did I say that backwards? If I'm a gray thing surrounded by white, I look darker. If I'm a gray thing surrounded by white, I did it backwards twice. Why am I writing this wrong? Contrast effect. It goes the opposite as the surround, which is why these are negative. Okay? But there are effects of your surround on the mean, meaning if you're surrounded by something bright, you look dark. So that's a first order effect. But a second order effect, if I have a pattern here surrounded by pattern, if the contrast of the surrounding pattern is high, then the contrast of the pattern in the middle will look lower. It'll look less contrasty than it is. So that's not about the mean gray level, that's about the variance. So if I'm surrounded by high variance stuff, my estimate of this variance, called contrast, will be low. If I'm surrounded by low variance stuff, my estimate of variance will be high. That has the horrifying term that Charlie Chubb, Josh Solomon, and George Sperling called contrast. Yes, whatever. George has a bad history of his many, 65 years of being in science, of coming up with terrible names for things, ones that would make Arrow cringe. In any case, so one can ask, did the variance in any of the pixels affect my response? And so this is no longer spike triggered averaging. This has to do with the variance, or potentially when it can expand the technique, it's called spike-triggered covariance. It's the kind of model that can estimate receptive fields of complex cells, not just simple cells, because it can deal with the fact that there might be some squaring and some interaction there. And so if you go back and look for how does the variance affect my response, you can see effects of the variance as well. So second order effects. I need to remind myself of where we're at. We're getting to the end of the day. I want to figure out when's the best place to stop. Good. So I'm not going to finish today, which is good. That will minimize how much I have to develop for Thursday. Oops. Of course, I forget when you do that. You can't do that. So first of all, it seems like a good model. I've given you a good reason why it gives you an unbiased estimate. There's math that says not only is it a good model, but it's a model that's easy to estimate. So math by Liam Paninsky suggests that if your function, we had this function that was the Poisson rate. We have the dot product receptive field, but we have this function. So if the function is convex, and by the way, sometimes you don't just estimate the function in general, like take that ratio I talked about. Sometimes you have a model for the function to reduce the number of parameters. So it may have some parameters theta that you're trying to estimate. So if the functions themselves are convex, accelerating, and if it's a convex function of the parameters that you're using it, and lots of models do that, then it turns out that the whole likelihood of this whole model with all its parameters is convex. Now what does that mean? Remember back when we had that diagram of fitting models to data, where if the model's convex, you can just roll a marble down the hill and find the answer. In other words, you can just hand your data and your model to fmin search, and MATLAB will do it for you, and MATLAB won't get confused because it can just go down the gradient descent, and get to the answer. So this model, under certain not terrible conditions, is convex, meaning that estimating it is not hard at all. You won't get stuck in a local minimum. So there's some nice math behind this model. And in particular, things like a Gaussian model works just fine, an exponential works just fine, a power function works just fine. So these models of the nonlinearity, which may have parameters that you're trying to estimate. So if you have a model for the nonlinearity, here are some obvious ones that you might have wanted to pick, and they'll work just fine, meaning no local min, easy to estimate. Next time, we're going to finish off thinking about these spike-triggered average models and ways in which they fail if you don't satisfy their assumptions and things you can do about that. And then we're going to move into a few other last end of semester topics. So I'm going to stop now 2 minutes early, and I will see you on Thursday.